This demo starts inside the App Connect container dashboard, where there's a new menu option on the left side called MCP Servers. We're going to create a new MCP server from scratch, based on ACE's huge catalogue of built-in connectors for third-party apps. We provide a name for the MCP server, and we stick with the other defaults for the license and the version of ACE. We've sped up the next part of the recording, as typically this next step might take a couple of moments. When the page loads, there's a huge catalogue of built-in connectors listed alphabetically. In this example, we're going to pick a couple of different apps, Slack and Salesforce. It's worth noting that I'm not having to engage with any kind of flow experience in this example that historically you might expect to see with an integration product. Instead, I'm just simply choosing which of these apps I want to connect to and providing some security details, such as the access token for Slack. Next up, we have the Salesforce option, which requires a bunch of OAuth details, such as a client ID, client secret, username and password. In the interests of time and through the magic of a recording, we don't have to wait and watch those values being copied into the blank spaces in the wizard. On clicking the Connect button, we're going to go off to Salesforce, check those credentials are successful, and when they are, we'll see the pop-up in the top right corner of the wizard. Now if we scroll back up to the top of the dialog page, you'll see that we've got an account that's been created using our security credentials, and there's a wide number of different objects and actions that are available within Salesforce, which we can expose as MCP tools. We'll expand Contacts and choose the Retrieve action. The numbers in the blue balloon shapes show how many MCP tools we're due to create. In the case of Slack, we'll select the option to retrieve a list of available public channels and the option to send a message to a channel. So in total, the final summary page is going to show us we've got 3 separate MCP tools exposed from 2 different back-end applications, Salesforce and Slack. When we hit the Create MCP Server button to finalize the wizard, the process of spinning up that integration runtime again can take a couple of moments, hence the warning in the wizard. So having completed that process, we can now see a tile representing the MCP server on the dashboard. Drilling down into the server, we can see the information telling us how to connect to the server, which we'll use in a couple of moments when using IBM Bob to invoke the ACE MCP server's tools that we've just created. On the other tab, we see a summary listing the exposed tools. The next stage of our demo switches to a similar looking web browser experience, except this is the web UI for the ACE software product, not in containers. There are 3 servers and one of those already has 3 deployed REST APIs. Let's look at the customer API and try out the Get Customers operation. The API response shows 3 customers who happen to share their names with 3 English footballers, Harry Kane, Gary Lineker and Jimmy Greaves. The JSON data gives basic name, address and telephone information. Next, we're going to navigate back up the hierarchy and return to the integration server level for server 1, and then go into the loyalty card API, where we'll find another operation to get loyalty cards. The response message shows that there are only 2 customers who have loyalty cards. The info shows their home store, membership tier and the number of points they have. Now we're going to take those REST APIs and expose them as MCP tools using an experience that will be reminiscent of the wizard we saw a moment ago. We're going to choose server 1, which hosts the REST APIs that we were just testing. We can choose the port number that the MCP server will expose, and then the next panel allows me to expand the available APIs and select some operations. I'm going to choose the 2 GET operations in the customer API, and then I'm going to choose the 2 GET operations in the loyalty card API. And again, you can see as I'm making these selections, the blue bubbles update with the numbers indicating those selections. We have some finally summary information and then click the Create button. Next, we're going to switch to VS Code, where we'll use IBM Bob to invoke the MCP tools. To save time, we've already configured Bob's MCP settings JSON file, but I display it here to prove that Bob has already been given connection details. Switching our attention to the IBM Bob chat interface and making it full screen, my first question to Bob is to ask him to list the MCP tools. Bob checks the configuration JSON file and makes queries to the 2 MCP servers and returns a detailed description of the 7 MCP tools that are available, 4 from the on-premise ACE environment and 3 from the ACE container environment. The next query we type in asks Bob to please retrieve the Salesforce contact with last name Kane. Bob already has the MCP tool context and knows the available tools, so there's no need for me to even mention MCP as part of this query. I also don't have to mention anything about ACE or have any knowledge of the underpinning infrastructure which is used to answer the question. The query goes through the MCP server and through ACE and gathers back a bunch of information about Harry Kane, including his date of birth, address, and a description. Next, we're going to repeat a similar query to find out about Jimmy Greaves. Again, the reply is laid out nicely once it completes here with about 10 bullets providing information from Salesforce all about Jimmy. You probably guessed what's going to come next. A final query of this type is going to retrieve information about our third footballer, Gary Lineker. Hitting on Approve makes the query go through, and we can see the response data has also come back successfully. Bob is now going to use the ID field from the Salesforce system to answer some more questions. For each of the retrieved contacts, find out if they're supermarket customers. In this example, the same IDs are actually used by both systems, but there are more complex cases where Bob can sometimes independently figure out the relationship between the taxonomy of different ID structures based on error responses or through further user interaction. In a similar fashion, Bob is now challenged to find out which of our 3 footballers have loyalty cards at the supermarket. This time the 3 replies give back slightly different responses. Harry Kane has a loyalty card, but the second query shows that Jimmy Greaves does not, and thirdly, Gary does have a loyalty card. And having received back that third response, Bob then takes all of the data that he's just retrieved and summarizes it together in a nice message that's been formatted and includes some icons showing ticks and a cross for the positive and negative responses. Our last task is to get Bob to summarize all the information in Slack. So we've begun by asking him to retrieve all of the Slack public channels so that we can figure out how to send a message to the general channel. The responses come back with the internal IDs and the human readable names of each channel. Checking inside Slack, we can see that there's currently no message there, and now we're going to ask Bob to send one through. Please send a detailed message to the general Slack channel summarizing everything you know about the 3 Salesforce contacts. So we're referring to the general channel in an easy human way without the need for those internal horrible IDs. We can see in the background Bob is generating quite a detailed summary message, which has got various icons inside of it, and then on clicking the Approve button once more, under the covers that will send the data off to Slack. Having seen the task completion dialog, we'll switch our focus to the Slack window and then look through the data that has just been sent across. You can see if we scroll up that there is information about each of the 3 contacts. We have some nice icons there to demonstrate their information, show whether they're customers at the supermarket, and also their loyalty card status. So this concludes our demo showing MCP tool exposure from both ACE in containers and traditional ACE software. This demo shows how you can now use an integration server running Java 17 to host flows that can read and write SOAP messages secured using the WS security standard. The Oasis Web Services security spec provides mechanisms to help web service developers secure SOAP messages. In summary, it describes 3 ways for securing web services at the message level: authentication, integrity, and confidentiality. Authentication uses a security token inserted in the request message to validate a user and determine whether a connecting client is valid in a particular context. ACE 13070 supports 2 types of security token for authentication: username tokens and X509 certificates. Integrity uses an XML digital signature to help the server protect itself, and confidentiality uses message encryption so that only services with the appropriate key can decrypt and read the data. We'll dive into the actual message flows using the Toolkit in just a moment, but first let's use this picture to orient ourselves. In our demo, we've chosen to deploy an ACE Web Service consumer to one integration server and a provider to a separate Java 17 integration server. Each of these servers uses a separate external directory vault to host the credentials which are needed to access its own key store and trust store and to sign and encrypt messages. Each integration server has also been configured with its own JKS key store, which are represented by the orange boxes in the center of the screen. Each integration server has also been configured with its own JKS trust store, which are represented by the yellow boxes in the center of the picture. This example uses X509 self-signed certificates, which we've already created and populated inside the key store and trust store belonging to the consumer and inside the key store and trust store belonging to the provider. Typically, configuring a public key infrastructure like this can sometimes be a bit tricky, but it doesn't make for a particularly entertaining demo, so we'll briefly share on the screen the various commands that were used in case you want to pause or revisit the recording later. We'll now take a brief overview of the message flows. Starting with the WS consumer, we have a SOAP request node who's already been configured with a WSDL file. On the HTTP transport tab, we can see the URL that we are going to invoke, secured via HTTPS. Switching to the WS extensions tab, we can see the relationship with the WS security policy called demo consumer that lives inside the demo consumer policies project. Exploring the provider message flow, on the HTTP transport tab, we can see the path suffix URL. We can also see that use HTTPS has been ticked, and there's a similar relationship, this time with the demo provider policy. We'll go back to the toolkit to play some data through in just a moment, but looking in more detail about how WS security is applied, there are essentially 4 steps involved. Number 1, the consumer encrypts the data using the provider's public certificate and signs the data using the consumer's private key. Next, in stage 2, when the data arrives at the provider, it decrypts the data using the provider's private key and verifies the data signature using the consumer's public key. After the flow has done its processing, which in our example involves converting a temperature between Celsius and Fahrenheit, similar steps happen in reverse for the return leg. In stage 3, the provider encrypts the reply data using the consumer's public certificate and signs the data using the provider's private key. In stage 4, when the data arrives back at the consumer, it decrypts the data using the consumer's private key and verifies the data signature using the provider's public key. We're now going to take a look at the policy configurations that are associated with the 2 message flows. The demo consumer policy XML file has 4 separate twisty sections of properties, one related to signing, another for encryption, and then the same thing for the opposite direction of data flow. Clicking the Configure button displays a dialog that will be familiar to ACE users from previous versions of the product. Now we have amalgamated the policy sets and bindings properties from earlier versions, this panel is required to list out the settings for message level protection and message part protection. We're choosing to encrypt and sign the whole message body, but if you wanted to do something more fine-grained with specific fields, the XPath expression page provides these options. Next, we'll switch our attention to take a look at the equivalent policy settings for the provider side of the relationship. The demo provider policy XML file has a type of WS security input, and down below there are the same 4 sections that we saw just a moment ago relating to message signature validation and message decryption, and then for reply message signing and encryption in the opposite direction. The Configure panel launches the more detailed dialog with settings for message level protection and message part protection. The message part protection page is configured for full body protection, just like we had on the consumer side. Having gone through all the configuration of the flows, we'll now see them in action. We've already deployed both the consumer and the provider message flows, but we're going to use the flow exerciser and place the consumer into recording mode in order to track the data as it flows through the scenario. The security provider message flow has already been deployed, but it's currently in a stopped state. And before we use that, we're going to use an alternate flow that I've named Simple SOAP Sniffer, which has a SOAP input node, and we'll also place that into the provider integration server, and we will put that one into recording mode as well. The purpose of this message flow is just to capture the headers that flow through from the consumer so that we can look at them in a nice easy fashion. Sending in the data with the temperature of 0 and expecting that to be converted, we will then exit from the message injection dialog and go take a look at what's happened. We can see the data made it as far as the SOAP request node, which invoked the sniffer flow, where we can go look at the data that arrived. If we go full screen, We can then see that from the context section, this SOAP input is in gateway mode. The header carries a WSSE:security header. Collapsing the header, we can also see the body of the SOAP message contained the encrypted data and also some cipher data at the end of the message. Examining the WSSE security header close up, we can see lots of details about the binary security token and the encrypted key. Remember, this sniffer message flow does not have any association with the WS security policy projects that we defined, and in gateway mode it has made no attempt to decrypt any of these values. Looking at this detail gives us confidence that all of our hard work configuring the flows has paid off and the payload has been correctly secured according to our wishes. In the toolkit, you can see that we've now stopped the simple SOAP sniffer flow and we're starting up the WS security provider flow. Placing this into recording mode on the demo WS provider integration server will enable us to track the real data as it goes between the consumer and now the proper provider. Returning back to the consumer flow, we'll click the Send Message button and send the same data in that we were using a moment ago with the sniffer. And this time you can see we've received back an HTTP reply message which has converted the temperature into Fahrenheit. We can see there 32 degrees in the response data, which is an excellent sign. We can then go and look at the path that the message has taken and see it went all the way through the flow. And looking at the demo WS security provider flow, tracing the path that the data took, we can then see that once all of the encryption has been dealt with and the decryption has been dealt with, we have a standard form of SOAP body with the temperature being carried back and then placed into the response message in readiness for the SOAP reply with the converted temperature. And so this concludes our demonstration of WS security in Java 17 integration servers. This demo shows the new batch process action in Designer that can go in an event-driven flow or in a REST API. Our scenario is triggered by a scheduler node and then ACE retrieves a set of contacts from Salesforce. This data set is passed into the batch process which runs asynchronous to the main part of the flow. In our scenario, we're going to use a Slack node to send a message indicating that the batch has started. The batch process iterates over the retrieved contacts and for each one invokes a REST API to find out if the contact is a customer of a supermarket. For convenience, we're actually using a REST API hosted inside ACE. This isn't particularly relevant, but lets us closely control how fast the API responds to help make this demo a perfect length. Info about each contact is then written to a separate message on a queue. Then at the end of the flow, we write another message to Slack summarizing the results of the whole batch. Here in Designer, we'll quickly examine the properties of each node in the flow. The scheduler fires once a day at midnight, and also when the flow is first switched on, which avoids us having to wait for the batch to get triggered. Before diving into the batch process part of the flow, which queries Salesforce, we'll next take a look at the Slack node, which will send a message to the general channel. The message text states that the batch process has been started and includes a timestamp with the current event time. The batch process section of the flow starts with a Salesforce node that has been configured to retrieve contacts. There is no further qualifying where clause in this example. If you'd like to, you can restrict the maximum number of contacts to retrieve, and there's also an option for generating an ID for each record in the batch. Back in the flow, you'll see there's a couple of icons to mark the beginning and the end of a section of behavior where the fanned out records go through the REST API call and then the if statement. The REST API invocation passes the ID of the Salesforce contact into the REST API so we can find out whether this specific contact is a supermarket customer. The if block that comes next examines a code which is a field in the API response data structure. If the code carries the value 999, then the MQ node that follows down the top branch will write info about the contact to a queue called sf.supermarket.notCustomer. Alternatively, if the return code from the API was not 999, then a matching supermarket customer record was found, and so the alternate branch of the if has an MQ node that writes to a different queue called sf.supermarket.customer. After the end of the batch process past the flow, we use another if statement that checks whether the number of records that process successfully match the total number of records. This causes a log node to write that all messages were a success. Down the other branch, we log that all messages were not processed correctly. At the very end of the flow, the second Slack node writes a summary message that also includes a log of the current time. Next, we'll rearrange the screen in readiness for running a batch of data through the message flow. Rearranging our windows, you'll note that there is a green screen and a blue screen, and these will be used to drain messages from the two output queues. We can see that to start with, there are no messages in Slack. In Designer, we select the option to test with real data, and then immediately following we'll choose to view the batch so that we can keep track of its status as it progresses. In the green window, we'll start the AMQS GET application running, and you can see we've already processed a few contacts who are not supermarket customers. In the blue window, we'll set off the same command looking at the other queue. We haven't reached any contacts who are customers just yet. Let's refresh on the batch status to see how we're doing. We were on 13 and now we've completed 14 of the 24 contacts. In the blue window, the app times out if no messages have been written for a few seconds, so we'll just run that command again. We've now hit some contacts who are supermarket customers. In total, we're expecting 3 of the 24 contacts who all share their names with famous ex-footballers for my team Tottenham Hotspur. All 24 contacts from Salesforce have now been processed, and we have 21 in the green window and 3 in the blue window. Next, we'll go back to the Slack application to check on the output there, and sure enough we can see that final summary message. The last thing that we'll do is to go take a look at some logs. There's a handy link from the status view that filters the logs using the name of the message flow. There's an entry showing the write to Slack, and if we scroll on further down, there are also some examples of writing to the MQQ for those who are not customers, and also the MQQ for those who are Salesforce customers. And so, in conclusion, we've seen the new batch process option in Designer in action, processing a set of retrieved contacts from Salesforce. This demo shows the new claim check feature in ACE, which efficiently transfers large payloads of data between apps without incurring a large memory overhead in the flow itself. We'll be using files in Dropbox and Salesforce, and as you can see, I've already created credentials for those apps in my server's external directory vault. We'll be using the message flow shown, which receives JSON data over HTTP. The inbound message will match to the highlighted JSON schema and will include a path to the file that we want to retrieve from Dropbox. The flow order node routes first to an HTTP reply and then invokes the Dropbox request node. Next, we'll jump into Connector Discovery to look at the configuration of the download file action in a bit more detail. As usual, we have a policy project used by the Connector Discovery process, and after a few seconds loading, we're going to look at the response controls. That includes a property for defining the way in which the node should handle binary response data. You can choose between the JSON domain or the blob domain for this property. The main action of the node has already been set up to download file. Returning back to the message flow view, the trace node comes next, which is configured to write to a file the current timestamp, and then the context reference function is used to display the in-memory tree that has been output by the HTTP input at the start of the flow, and then the output from the Dropbox node. This will let us demonstrate that a claim check token is passed from the Dropbox node to the Salesforce node, avoiding the actual file content coming into the flow. The last node in the flow is the Salesforce request. The map shows that the Salesforce file content has been assigned directly from the file content structure that came out of Dropbox. The title property is used to name the file and is calculated using the substring function, which takes the file name characters from the end of the path property, which arrived as part of the initial JSON input message. We're starting from an empty integration server, so next we'll deploy the claim check policy project by dragging and dropping it onto the test server. Next, we drag and drop deploy the claim check application itself which has the message flow inside of it. In order to test out the flow, we'll rearrange our windows to show the available files currently preloaded inside Dropbox in the browser window on the middle left of the screen. The bigger Salesforce browser window on the right shows there are currently no files owned by me in the Salesforce platform. We'll use the command console at the top of the screen to invoke the message flow using curl. The input data carries the path to a PowerPoint file named pres_approx1mb. Our trace file has been written to disk, and refreshing the Salesforce view shows the file has been successfully retrieved and copied over. We've now repeated the command for transferring a second PowerPoint file. This time it's 5 megabytes in size, and finally we run the command for a third time with a 10 megabyte file. Now we've moved 3 files, let's examine the content of the generated trace file, which has 3 sections of data, each with timestamps matching what we've just run through the system. You can see there is a file content item in the tree with a new type called claim check. For informational purposes, the text tells the user that the token originated from Dropbox. This is handy in more complex flow situations where you might have multiple claim check tokens being passed around. Back in Salesforce, we can select the 1 megabyte file and Salesforce will preview the contents after a few seconds. Having proven that the flow worked successfully, we're now going to delete the 3 files from Salesforce. For this demo, I'm working in a Developer Edition account, which constrains me to a maximum total of 20 megabytes of storage space for files. In a moment, we're going to try out some bigger files, and I want to avoid potential errors from Salesforce by going over the limit, so let's clear down the 1, 5 and 10 megabyte files. For this last section of the demo, I'm going to bring up Windows PowerShell, where I can loop around the get process command every second and report on the working set memory being used by the integration server process. I'm going to leave that running while we go back to the command console window at the top of the screen and send in a new request to retrieve the next file size, which is a size of 20 megabytes. I'm then immediately going to repeat the curl command and send in a 50 megabyte file as well. And although this will push me over the Salesforce file limit, it's normally gracious enough to give me one last file as I blow through the limit, especially if it's in quick succession. If we refresh the browser, after a couple of seconds we should see both files have appeared. Taking a look back at PowerShell then shows the memory of the server has only increased very slightly and nowhere near the size of the files that have been successfully streamed directly between Dropbox and Salesforce. So in summary, we've seen the new ACE claim check feature that efficiently transfers large data payloads directly between applications.